everyone, welcome to the today's session. I am Priyanka Agarwal, a PMRF scholar at Chemical Engineering Department at IISc Bangalore, and I am taking these problem solving sessions for the course Differential Equation for Engineers, which is taken by Professor Srinivasa Manam from IIT Madras at NPTEL. So today we are here in week 11 and we are going to solve some examples related to the heat equation. So let's start and I'll mention the first question over here. So the first question is, find the solution for the to the following partial differential equation. So the partial differential equation is del u by del t equals to k del square u by del x square, and we are given the initial conditions and the boundary conditions. And boundary conditions which are u at x comma 0 equals to some function of x, and u at 0 comma t equals to 0, and u at l comma t equals to 0. Okay, so to solve this, first thing technically what we need to do here is to apply separation of variables, and we have seen several examples of applying separation of variables in our previous sessions as well as in the main lectures. Okay, so to solve, let's assume that the solution will take the form u x comma t is equal to some function psi of x into some function g with respect to time. So what we are doing here is we are using separation of variables. I'm not feeling well today, so I might not be able to speak properly at few times. Pardon me for that. Okay, so now we have to apply this transformation to the given equation to solve it. So let's plug it in this thing into the given differential equation, and let's see what do we get. Okay. So what do we have here is del by del t of u, which is, I'll drop x and t here. Okay, psi and g equals to k del square del x square del into g. So here it becomes del g by del t equals to k g del square psi over del x square, right? Now Let's divide by psi into g. So what do we have here is 1 by g del g by del t equals to k by psi into del square psi over del x square, right? So we have this form. Now let's divide by k. Then the given equation takes the form 1 by k g del g by del t equals to 1 by psi del square psi over del x square. So this is a function of x only and this is a function of time only. So we can write it as some constant, let's say minus lambda, where this is called separation constant and this is going to be some arbitrary. Now the next question in this would be, why the minus sign? Again, because minus sign doesn't have to be there, and in fact there are times when we don't want it there. So how should we know, how do we know that whether it should be there or not? And so answer to that is to proceed to the next step in the process, which we'll see soon, and at that point we'll know if it would be convenient to have it or not, and we can come back to this step and add it in or take it out depending on what we choose to do here. Okay, so let's proceed with this process, and so the next step would be to acknowledge that we can take the equation above and split it into the two ordinary differential equations. So let's split it. So the two ODEs in which it can be split is now 1 by kg del g by del t equals to minus lambda and 1 by psi del square psi over del x square equals to minus lambda. Now this becomes del g over del t equals to minus k lambda g and del square psi over del x square becomes minus lambda psi. So this is what we have right now. Got it? So once we are over here, so both of these are now very simple differential equations, but because we don't know the value of lambda, we cannot solve these easily, right? So this time equation could however be solved at this point if we want to, although that wouldn't always be the case. So let's see how to solve this equation. Okay, now we have these two equations. Now also see the boundary conditions, what they have become. So we know the boundary condition is u at x comma 0 is fx and so this is the initial condition, and boundary condition is u at 0 comma t equals to 0 and u at l comma t equals to 0. So what will be the condition over here? Now let's see boundary condition, which is u at 0 comma t is 0. So what does this mean? That psi, which is a function of x, that is now 0, and g, which is a function of t, equals to 0. and the other boundary condition is u at L comma t is equal to 0, which means that psi at x equals to L and g at some time equals to t is equal to 0. So this is what we have. So now let's consider this for a second. Now we have two options. Either this could be 0 or this could be 0 for every t. However, if this becomes 0 for every t, then we will have u x comma t equals to 0, and this becomes the trivial solution, which is not what we are looking for. So here in this case, psi of 0 will be 0. So this is one boundary condition which we have now in terms of these separation variables. Now similarly, if we look at over here, for the same arguments holds true, and we have psi at x equal to L equal to 0 as our second boundary condition, right? Okay, so these are the boundary conditions which we have. Now we have to solve this equation for several cases, and so let's say there are three cases, okay, where lambda could be greater than 0, okay, and lambda could be equal to 0, and lambda could be less than 0. So these are the three cases which we have as of now. Now let's take the case 1. Let's look at the initial condition also. So initial condition says mu at x comma 0 equals to some f of x, and so this will become psi at any x into g at n times 0 equals to f of x. Now similarly, we can argue for this, that if this becomes 0, that means that u at x any position for all times will be then 0, which is not the case, then g at 0 is equal to 0. So this is our initial condition. Alright, now let's solve step by step. Let's take the case 1 where lambda could be greater than 0. So in this case, if you look at the equation for psi, this and what the solution becomes. So the equation what we have is del square psi over del x square equals to minus lambda psi, right? Now the solution becomes phi at any x equal to c1 cos root lambda x plus c2 sin root lambda x. Now apply boundary condition, that is psi at 0 equal to 0. What it becomes is 0 equals to sin 0 is 0, so cos 0 is 1, so it becomes c1. So c1 equal to 0. And now apply the second boundary condition, which is sin at x equal to L is 0. So what it becomes is 0 equals to c1 cos root lambda L plus c2 sin root lambda L. Now c1 is 0. So what does this become? c2 sin root lambda L equal to 0. So From this, what we know is that either C2 equal to 0 or sine root lambda L equal to 0. This cannot be 0, otherwise we will have a trivial solution, right? So therefore what we have is that sine root lambda L equals to 0. Now when we have this, what we can write, this as when is sine of anything 0, then this thing equals to n pi. So now we have root lambda L equals to n pi, right? Where n equals to 1, 2, 3 and so on. So, okay, so this is the solution in this case. So the eigenvalues, that is the lambda is the eigenvalue. What will it become? So we can write n equals to, we can write lambda equals to, root lambda equals to n pi by n. So lambda n, this can be written as lambda n. So lambda n square can be n square pi square over L square. Therefore, psi x can be written as some constant C2 sine of this value. So C2, for now let's consider it as 1. So this becomes sine n pi by L sine lambda n x. Okay. So this is our eigenvalue and this is our eigen function. Alright. So this is the solution. Now let's take the case 2 when lambda equals to 0. So this is very simple equation. It becomes del square psi over del x square equal to 0. So in this case, psi of x becomes c1 plus c2 of c2 times x. Now if we apply the boundary conditions in this case, so boundary condition, if we apply it over here, which is psi of 0 is equal to 0. So what will it become? That c1 equal to 0. And another boundary condition is psi of L equal to 0, which becomes c2 into L, that provides c2 equal to 0. So in this case, the only solution is the trivial solution. Okay, it is the trivial solution and therefore lambda equal to 0 is not an eigenvalue for this problem. Okay. Now we have looked at two cases. Now let's take a look at the case 3, the case in which lambda is less than 0. In that case, the solution will become psi x equal to c1 cos hyperbolic minus root lambda x minus will be inside the root minus root lambda x plus c2 sine hyperbolic root of minus lambda x. Now apply the boundary condition psi of 0 equals to 0. What do we get? So this becomes 0. So what do we get it? C1 equal to 0 as the cos hyperbolic of 0 will be 1. Now applying the second boundary condition, what do we get? C1 is 0. So this is 0 plus C2 sine hyperbolic minus root lambda L, right? Since we are assuming that lambda is less than 0, okay, so in this case, we are assuming that lambda is less than 0. So minus lambda will be greater than 0, right? And therefore, L of minus root lambda will not be equal to 0. Therefore, if this is not going to be 0, that means sine hyperbolic L of root minus lambda cannot be 0. Therefore, in this case, we must have C2 equal to 0, right? Because either C2 equal to 0 or this term equal to 0. This cannot be 0, therefore this has to be equal to 0. Therefore, we get trivial solution. Trivial solution in this case. Okay. So therefore, what can we say? Therefore, there will be no negative eigenvalue. There will be no negative eigenvalue eigenvalues for this boundary value problem, and therefore eigenvalues are lambda n equals to n pi by l square, and eigenfunction is psi l x equal to sine n pi x over n, and where n equals to 1, 2, 3 and so on. Okay. Now let's solve the equation in time. Now let's solve dg over dt equals to minus k lambda n into g. And now note that even though we now know lambda, we are not going to plug it in quite yet to keep the miss to a minimum. We will, however, now use lambda n to remind us that we actually have an infinite number of possible values here, because lambda n has infinite possible values. Now this particular equation, it is a simple linear first order differential equation. So the solution for this will be of the form, I'm going to write it directly, c into e to the power minus k lambda n t, and this can be written as c e to the power, I'm going to write it this way, minus k, lambda is n square pi square over n square into t. Okay, so now we have written the solution for both the ordinary differential equations, one in terms of psi and another in terms of g. So therefore, u n x comma t can be written as, so this constant and the constant in that equation we can combine, and let's write it as some constant bn sin n pi x over l e to the power minus k n pi by l square into t, where n equals to 1 to 3 and so on. So this is the final solution which we have. Okay. I hope the solution is clear to everyone. If not, please let me know. Okay. Now based on this, let's solve another question where you have to solve the heat problem for the given initial conditions. So you have to solve del u over del t equals to k del square u over del x square. So this is the heat equation, and the initial conditions are u at x comma 0 equal to fx, u at 0 comma t equals to 0, and u at l comma t equals to 0. So essentially we now know that the solution is this. So this is the solution. Okay. Now we have to solve it for different values of fx. So for the case when fx is equal to 6 sin pi x by l, let's solve and see. Okay. So now in this case, let's see how to write the solution. So basically your x comma t is equal to bn, to this thing, bn sin n pi x over l e to the power minus k n pi by l square into t, right? Now if fx given to you is this function, see this thing. So we knew that so this is some blunder I have. This is not true. Okay. Okay. So in this case, if you compare with the given thing, so this is a function x, so this is some term of psi, and psi was some constant into sine lambda root lambda times kind of thing. Okay, so you can substitute over here. B is 6, and since lambda was like n pi by l, right? So here n can be chosen as 1. So n equals to 1, and therefore b1 equals to 6, right? So what the solution will become is, if you just compare this with this given form, okay? So now your x comma t will become 6 sin pi x by l e to the power minus k pi square over L square into T. And this is the solution which we need. Okay. Now you check. If you put T equals to 0, then u of x comma 0 becomes e to the power 0 is 1. 6 sin pi x by L satisfied, right? You put x equal to 0 over here. Then ux comma t becomes 0, right? Similarly, if you put x equal to L over here, then this becomes u x comma, so 0 comma t. Now this becomes L comma t. So this is 6 sin now pi into e to the power something. Sin pi is 0. So this also becomes 0. So this is the required solution. Now for this only, let's consider another case where your fx is 12 sin n pi x over L minus 7 sin 4 pi x over L. Okay. So let's consider that this is the case. Now fx is this. This looks much more complicated than the previous case, right? It has second term also. But this is also almost as simple as the first part, and just we use the principle of superposition that if we have two solutions to a linear homogeneous differential equation, so these are the two solutions, solution 1 and this is the solution 2, then their sum is also a solution. So what do we need to do is we need to choose n and bn as we did in the first part, and to get a solution that satisfies every solution, right? So we will use principle of superposition. Use principle of superposition here. There will be two solutions to a linear homogeneous differential equation, then the sum is also a solution. Okay, so we use that property, and if we use that property, then what do we got here? For this case, first case bn will be 12, and then we have the sign n pi x over L. So in this case, we have this bn equals to 6 and n equals to 9. Okay. And this becomes into e to the power minus k 9 pi by L. 9 pi by L square into t minus, in this case, what we have is this solution 4 pi x by 2 e to the power. So in this case, bn is now this 7 and n equals to 4 in this case. This is b4 and this is b6 e to the power minus k. Okay. And this term I will write it down here, e to the power minus k. This term which is 4 pi by L square into t. Alright, so this is the required solution. So now we have seen that a solution that it satisfies any solutions for the initial condition in the given boundary conditions. Now let's try to solve another problem. Okay. So in this case, what we have seen here is okay. So far we have seen these solutions, and now let's extend this idea when that we have used in the second part of our previous example a little to see how can we get a solution that will satisfy any sufficiently nice initial condition. So we'll use principle of superposition over here, which is uh, not restricted to only two solutions, but multiple solutions also we can use, and therefore we can write our final solution in form of a series. Okay. So now for this only, solve the following boundary value problem, which is del u by del t equals to k del square u over del x square, and we are given that u at x comma 0 equals to 20 and u at 0 comma t equals to 0 and u at l comma t equals to 0. So these are the conditions which we have. Okay. So by simply extending the idea from the previous problem, you can write the solution as the sum of series, which is basically the principle of superposition over here. Real sum n pi x over a e to the power minus k n I over l square into t. So this is the solution which we have. Now we have to write the coefficient. We have to find the coefficient over here. So the coefficient can be written as coefficient 2 over L 0 to 20 sin n pi x over L dx, which is equal to 2 by L. This becomes 20, you can take outside, and this becomes 20 L 1 minus cos n pi over n pi. This is after applying the limits. So this becomes 40 1 minus 1 to the power n over n pi. And if we write this in the given in this particular solution, then we will get the final solution as 40 into 1 minus 1 to the power n and suppose n pi. So this is our dn, and then we have this sin n pi x over l e to the power minus k n pi by l square into t. So this is the required solution in this case. Okay, let's try to solve another question. Here you have to find a solution to the following partial differential equation. Which is del u by del t equals to k del square u over del x square u at x comma 0 equals to f of x and del u over del x equal to 0 comma t equals to 0 and del u over del x at l comma t equal to 0. So now we have to solve this particular equation. Now you see the change in the boundary condition. Now they are not on u but they are on del u by del x. Okay. So we have to solve this particular question now. So here we can assume that our solution is of the form where ux comma t can be written as sin of x into g of t. As in the previous problem, you can use separation of variables here. And so I will straight away directly write down the equations. So ODEs found in this case will be dg over dt equals to minus k lambda g, and the other will be d square sin over dx square plus lambda sin equals to 0. And the boundary condition becomes del psi del x at x equal to 0 equals to 0 and del psi over del x at x equal to L is equals to 0. Okay, so we solved the boundary value problem in the previous example where we solved using eigenvalues and eigenfunctions. So similarly, we will try to solve here. So here also we can have three cases. So let's see for the case when lambda is greater than 0, then psi can be written as C1 cos root lambda x plus C2 sin root lambda x. So if we apply the boundary condition, which is del psi over del x at x equal to 0 is 0, and what do we get? 0 equals to, this will be C1 sine of this, sine of root ix, okay, into root lambda and with the minus sine, and then the other way plus cos root lambda x C2 root lambda. Okay, so if x equal to 0, this is 0. So what do we, this becomes this. Now what do we have here is 0 equal to C2 root lambda. Lambda cannot be 0, so C2 has to be 0. So C2 equal to 0. Now we apply the other boundary condition, which is del psi over del x at x equals to L, which is equal to 0. Now what do we get here in this case is 0 equals to minus root lambda C1 sine root lambda L, right, plus the other term is C2 something which is 0. So from here what do we get is C1 sine root lambda L equal to 0. So if C1 equals to 0, then we will get, what we get is a trivial solution. So this cannot be 0. So therefore L root lambda equal to 0. Sine of L root lambda equal to 0. That means this is equal to sine of n pi. Therefore L root lambda equals to n pi. Lambda is, L can be written as n square pi square over L square, where n equals to 1, 2, 3 and so on. So this is the eigen value. The eigen function what does it become? Then psi n x can be written as now cos or n pi x over n. Right? Any doubts still there? Please let me know. If not, we will move to the next case where lambda is equal to 0. In that case, as you saw earlier, the solution was C1 plus C2 x. Now if we apply the first boundary condition like del psi of del x at x equal to 0 equal to 0. So let's write del psi by del x, which is C2. So this would imply imply that C2 equal to 0, right? Therefore, and del psi by del x at x equal to L equal to 0. This also means C2 equal to 0. So therefore, psi at x equal to C1. Now note that this will trivially satisfy the second condition, this particular thing. You also see that it's satisfying. Therefore, lambda equals to 0 is an eigenvalue for this boundary value problem. Okay, and the eigenfunction corresponding to this eigenvalue is psi of x equal to 1. I hope things are clear till this point. Now let's look at the case when lambda is less than 0. So the general solution can be written as psi x equal to C1 cos hyperbolic minus root lambda x plus C2 sin hyperbolic root of minus lambda x. This is clear. Clear? Now apply boundary conditions. Okay, so then psi by del x at x equal to 0 is 0. So let's write d psi over dx in this case. C1 root of minus lambda minus sin hyperbolic root minus lambda x plus C2 root minus lambda cos hyperbolic root of minus lambda x. Okay, so if we apply this particular boundary condition, if we just substitute x equal to 0, this term vanishes and this becomes 1. Then we have a 0 equal to C2 cos hyperbolic. So this becomes 1. So we have C2 equal to 0. Now let's apply the second boundary condition. If x equal to L, L psi by del x equal to 0. What do we get? 0 equal to C2 0. So this term has gone. Now this is minus C1 root minus lambda sin hyperbolic minus lambda root x. Right? This is what we have in the second boundary condition. Okay. Now as we did in the first example, we also do the same thing here. Now we know that lambda is less than 0. Minus lambda is greater than 0. Right? Therefore, root of minus lambda is greater than 0 and root of minus n is greater than 0. Okay. Now when we know this, we know that sine of this will be not equal to 0. Therefore, we have C1 equal to 0. Hence, we can write that this boundary value problem will have no negative eigenvalues. Okay. So, if we write the complete list of eigenvalues and eigenfunctions for this problem, what do we have is lambda n equals to n pi by l square, and for this we have psi n as cos n by x by n, where n equals to 1, 2, 3 n. So, and the other is lambda 0 equals to 0. This is n. Okay. Now let's solve for g. It becomes g of t equals to c a to the power minus k n pi over l square into t. So the product solution will be ul x comma t equals to some constant a n cos n pi x over l e to the power minus k n pi over l square into t, where n is equal to 0, 1, 2, 3 and so on. Therefore, we can write solution as u at x comma t equals to summation n equals to 0 to infinity a n cos n pi x over l e to the power minus k n pi over l square into t. Now apply initial condition in this, which is u at x comma 0 equal to fx. We put that e to the power 0 is 1, and this becomes summation n equals to 0 to infinity k cos n pi x over n. So we can see that this is nothing more than the Fourier cosine series for fx on when x lies between 0 to l. And so again we could use the orthogonality of the cosines to derive the coefficients, or we could recall from the lecture also. So using orthogonality, what do we have? An is 1 by n 0 to l fx dx, where n equals to 0, and this becomes 2 by L 0 to fx cos n pi x over L dx and not equal to 0. Okay. This is the final solution. This is the solution and these are the coefficient values. Okay. So if you have any doubts, please let me know. We are done for today. So if you have any doubts, please let me know. Otherwise, we will close the session for today. So the next week will be the last problem solving session. I hope to see all of you there. Thank you for joining me today. Bye bye.